Swayam Prabha. Digital India. Educated India.
Let us get started with thermodynamics. And you know that thermodynamics is taught in the undergraduate first year class, and this is one of the most important scientific discipline that people have ever discovered. So the topic is therefore thermodynamics. And the subject as it stands today is pretty old. And if you go back to its genesis, then you will see that it had its beginning in the Industrial Revolution in the latter half of the 18th century. So the Industrial Revolution So this scientific revolution in the second half of the 18th century that actually changed a lot in our understanding of what is science today. So people discovered many new things. One of the important things was revolutionize the communications. That was the telegraph that was discovered. Then there was a spinning wheel that was discovered. And the most important thing was the steam engine. So that made a revolutionary change in the process of transport. So human labor was actually replaced by machines. So that was the crux of this industrial revolution. So the point is that there are the byproducts of these industrial revolutions were basically the telegraph, then spinning machine, and last but most important is steam engine. So this steam engine is actually this played a pivotal role in our understanding of thermodynamics. So how that is to be discussed today, and that is the beginning of our understanding of thermodynamics, and that was the main inspiration behind it, actual applicational inspiration that you might talk about it. So what this steam engine means, that you have some water inside a container. It's a large container. You put in your water inside, and what you do, you heat it up. Once you heat it up, then water vaporizes, and then that it gives pressure. And once it gives a pressure, and if you have a piston, then it can move forward. So under high pressure, a piston can move forward, and when you release the pressure, the piston moves backward. So water is something that is used as a working medium to push a piston towards in the forward direction, and when the pressure is released, it comes back to the initial position. So this to and fro movement of a piston which encloses, which is actually coupled to a container, then what happens, and you can transfer this, you can connect the piston to a rod and then to a flywheel, and then you can rotate that particular wheel. So that was the important thing. So water is something that is important. Water as a working medium, water is used as a working medium So what you do, you use heat to vaporize this water, and that gives pressure, that generates pressure, and pressure uses, then that pressure shifts a piston, and the piston, as it moves, and when the pressure is released, it gets backward. Then what you get some amount of work out of it. That is, the to and fro movement of a piston actually can be converted into a linear motion, and that motion can be understood in terms of work. So what is there inside is that the heat is converted to work using water as a working medium. That was the basic principle of steam engine. So if that is so, then the heat and work, they are two important things that two important notions that we must take care of. What is meant by heat and what is meant by work. As you know, that this work is a concept that was derived from mechanics from long ago, and that was in the development of mechanics since the time of Newton, Laplace, and other people. And after the discovery of classical mechanics, this concept of work has actually got a very strong foundation in our in science. But heat is a concept that was new, and at that point of time, it was not realized in its actual sense. So heat is something, how it is related to work has to be understood. And thermodynamics is a subject which actually tells us about this, how this heat can be converted into work for the betterment of for the machine, and how to use heat to get useful work is something to do with the working of a machine. So that is the thing that we need to do. So that is the first thing, that so how heat is related to work, that is the basic thing. So next, so this is all about something about, I should not talk about that this is all, but it is something about a little bit of history. So this is basically, now if we want to work out the relation between heat and work, we need to do some more controlled experiments. So one English scientist who did it, that he was Joule, he performed some interesting controlled experiments on to understand the relation between heat and work. So Joule, between 1845 to 50, worked out several experiments. They did several experiments that relates the heat with respect to work. So let us see what it is. So relation between heat and work are the things. So how they are related. So the first experiment is sometimes called the paddle wheel experiment. So what this experiment is, let us talk about it. So we need a working medium. So the working medium is, say we take 100 gram of water. Say this is, I take 100 gram of water. So say 100 grams water. So this is water. So it is kept inside container, and what we have a wheel. and the wheel can be rotated along this axis, and if I fix it, if the rod is fixed through it, and I can rotate this particular wheel using a string, this is a wheel, and we have a thread and a mass that is put at the end, tied to the end. So what we have in mind, that if we allow this mass to fall freely, then it rotates this particular pedal, and that creates a turbulence inside the water. And now you have a state of water. I have taken 100 gram of water, and say this is at the pressure, say, is 1 atmosphere. Say I keep the pressure in 1 atmosphere, and pressure equal to 1 atmosphere, and say the temperature is basically 25 degrees centigrade. So it turns out to about 298 degree Kelvin. That is about 25 degrees centigrade. So this defines the state of water inside. And now what we do here, what you do further, you just have a adiabatic wall outside, so there is no interference of anything from outside. So that is an adiabatic wall. That is an essential thing. And what you do also, you put a thermometer here. This is a thermometer that is being put up here. So what I do, I keep water, 100 gram of water inside at a definite state, a stated pressure at 1 atmosphere, temperature at 298 degree Kelvin or 25 degree centigrade. Then what I allow this wheel to rotate by a free fall of this mass. So if the mass is m, then m mass times height times the acceleration due to gravity, that is mgh, that gives you the work done by this wheel on this particular water inside. So it rotates, and it happens that its state gets changed. And what happens? It gets temperature gets higher. So I can adjust my mass and height, adjust mass and height in such a way that I can keep my temperature at a different temperature. That means if this is my initial state, I can allow a change of state such that the pressure for the same 100 gram, pressure is now exactly same, 1 atmosphere. Temperature is now say 35 degrees centigrade. So it is 308 degree Kelvin. So there is a 10 degree rise in temperature. So what does it mean? That I have initially a state of the system. This is the state of the system, and the state of the system has changed to a new one, but the pressure remains the same, the temperature has changed. So whatever change that I have incorporated inside the system is something through two parameters, temperature and pressure and temperature. So they are actually the quantities that specifies the state of a system. Now, what is a system? System is the water, 100 gram of water that we have put inside this adiabatic container. So that is the basic thing. So there is a change of state here, and so how to describe this change of state? And this change of state is effected just by use of a work and nothing else. So the change of state is only due to your work W, and that is basically mgh, a concept that we have already mentioned, that is derived from classical mechanics. So if I assign that there is something in this state, some characterization for this state, if I call some energy, so and this state has another energy, so the energy difference between the two, say this is the initial state, this is the final state, so this is the final state, and say this is the initial state and this is the final state. For this state, I have a energy, say E1, I call it internal energy, and for this there is another state. For this state, I have the energy E2, both are intrinsic to this 100 gram of water. So this change of state, I can relate this E2 minus E1 is equal to W, and that is equal to mgh under adiabatic condition. So we have introduced some characteristic of the system that is called internal energy, and internal energy is something which is basically a function of pressure and temperature. Here is also a pressure of temperature, and for a fixed mass of water or the fixed mass of a system, and whatever change that I have brought in for the system is because of the work done by some external means on the system. So I have done some work on the system, and this is that work can be measured mechanistically by mgh, and that is basically related to two things, but the most important thing, it is under adiabatic conditions. In fact, Joule performed many experiments under adiabatic conditions. So adiabatic condition is a primary thing, otherwise we could not write this equation. If there are interventions from the other external agencies, it would not be possible to write down this kind of simple expression. Using that internal energy can only be accounted by some work that is done outside. So whatever outside is there is called the surrounding. So the 100 gram of water which has been kept inside is basically the system, and whatever remains outside is outside the adiabatic wall, it is the surrounding. So the surrounding, as if some work has been done in the surrounding, and that has been put into the system, and that raises the change of internal energy from E1 to E2. And that we can equate, and if this equation is basically stated some form of the first law, some form of the first law of thermodynamics. But let us check that whether I can do the same change of state in a different way. So can I do it? The same change of state in somewhat different way. So let us see, is it, so this is not the only way that I can change the state from E2 to E1, that is from P1 PT to another PT. This is not the only thing. So another way of the change of state. So we perform, or we change the state by a different means. So what we do, we take the same 100 gram of water. So you take the same 100 gram of water, same 100 gram of water, and 1 atmosphere pressure equal to 1 atmosphere, and temperature is say 298 degree Kelvin, and same state. This is basically the same state I am keeping the system. Now what we do here, the same system, I put it in a larger heat bath which contains a large volume of water. Say it is, I keep it here 1000 grams of water at say 80 degree centigrade. So this is a large volume of water. And there is no adiabatic wall between the system and the surrounding. Surrounding means the enclosure that contains water 1000 gram at 80 degrees centigrade. So when I keep that 100 gram of water at 25 degrees centigrade here, then what I see that there is a change of state inside, exactly the same, and I allow the change of state in such a way that I wait till the temperature goes to 308 or 308 degree Kelvin, and what happens to the system. So it happens that in the surrounding means that the large heat bath, say it has the initial state 1000 gram water at 80 degrees centigrade. When I put that 100 gram of water at 25 degrees centigrade, there is a change of state outside the system, and say the same 100 gram, same 1000 gram becomes 79 degree centigrade. That there is a 1 degree drop in temperature in the surrounding. That system has the surrounding has changed from 80 degrees centigrade to 79 degrees centigrade, and I see the same change of state, exactly the same change of state inside the system. So, same change of state means pressure is 1 atmosphere, temperature is 308 degree Kelvin. Again, this is the energy E1, this is the energy E2, as I assigned here, E1 and E2, same two states, but the change of state for this system that we have obtained in a slightly different way, that I have put a large, put the particular system inside a large heat bath, which I call it surrounding, and there is a transfer of something that we call heat, because I get the same change of state, and you see that the change in internal energy E2 minus E1, that is basically something that I call Q. I cannot write it exactly in this way, it's a mgh, because there is no mgh. For mgh, there is no provision, there is no work done on the system. What has been done, that as if something has been transferred has been exchanged in between the two, between the system and the surrounding, across the boundary of the system. This is the boundary of the system. So, across the boundary, that something has changed and something has been transferred, we call it heat for the same change of state. And no work done. In this case, this is under adiabatic condition, and this is under without any particular work. So, any change of state is entirely due to the flow of what I call heat, and as if 1000, it means that 1000 units of heat, 1000 units of what I call heat or Q has flown into the system. So, 1000 units of heat, and 1 unit we call 1 calorie. So, for 1 calorie, 1 unit is equivalent to 1 calorie. So, that is basically the introduction of heat and how this heat has been used to make a change of state of a definite system, kept under certain condition of temperature and pressure. And I see that the same change of state can be done in a different way, either by putting work into the system or by allowing some heat flow into the system. So, in both cases, we see that there is a law, that there is a change of state, and this change of state can be characterized by the change in internal energy, and that is equal to the heat flow, and this equality is possible only when there is no other intervention of work, and that is basically the heat. So, this is the heat, this is the work, that we have introduced, and we see how they are actually related. So, Joule tried to understand the two things, that for a same change of state, we can do either in terms of work or in terms of heat, but how they are actually related. They are not equal, that is, W is not equal to Q, although it seems that E2 minus E1 equal to W and E2 minus E1 is equal to Q. Does it mean they are equal? Not that they are not equal, but they are equivalent. So the next thing that we want to make certain qualification for the statements that how this heat and work are related, how Q and work are. As you see, it is tempting to write since E2 minus E1 is W and E2 minus 1 is Q, so W equal to Q. So, but that is not the thing, because this has been done under an adiabatic condition, and this has been done when no work has been done. So the conditions for their applicability are different. So, but they are equivalent. So W, so they Q and W are not equal, but equivalent. So they, and that is stated in terms of a simple relation that is called W times JQ, and J is called the mechanical equivalent of heat. That means they are not equal but equivalent. That is called mechanical equivalent of heat. So that is an important thing, but these are something that already there in the class 12 textbooks and other things. But there are concepts which are to be clearly understood, that the heat and work are not the properties of the system for which I can characterize it in terms of certain parameters, but they are the quantities. Heat and flow are the quantities that flow across the boundaries of the system and the surrounding, which separates the system and the surrounding. And I can add heat into the system or extract out of it, but that has nothing to do with the property of the system. So it is not a property. So W and Q are not the property. So Q and W are not the properties of the system, they flow across the boundaries of the system and the surrounding. So that is this is the main statements that we want to. Now I come to an important statement, that when I do some work on the system, or I add some heat into the system, and if I try to extract out some work out of it, then I have both the processes. So if it happens, now when I lift the adiabatic condition and no work done condition, if I lift it, then what should be the ultimate equation for delta E? So that is the thing, that if now Q amount of heat is added to the system, and the system does W amount of work, then I can write that E2 then the change of state can be given as E2 minus E1, that I call delta E, some change of internal energy, that is heat is added to the system and the system does some work, then I write it Q, that is added to the system, and minus W, that means system enjoys some facilities and from the system. So I subtract this something W. So this is delta E is Q minus W, is basically called the first law of thermodynamics. When both the adiabatic condition and no work condition are not there. So what we did, we tried to understand the relation between heat and work for a definite change of state. Then I understood what is the change of state, how can it be characterized. So to characterize it, I needed some internal energy, and that internal energy change has to be equated to either to heat or to work in an appropriate way. If I put the adiabatic condition, then that is only the work is the only thing that can be equated to E2 minus E1. And if the no work is done and some Q has flown into the system, then E2 minus E1 is the Q. But when both these conditions are lifted, then we have the situation where you add some Q amount of heat into the system and the system does W amount of work. Then we have delta E that is equal to Q minus W for a finite process. This is for a finite process, because for any given change, say 10 degrees centigrade, 20 degrees centigrade, some finite process, this is the law and we call it the first law of thermodynamics.